This work was done by my student Xuesong. She just have a baby, premature baby, so she cannot come here. So I will present this talk for her. Well, I recommend to name the baby sensors, but maybe that's not a good idea. As usual, the professor doesn't really know everything what the student do, so I try to make this talk as simple as possible. Of course, there are a lot of details only the student will know. Starting from beginning is the sensor has the PS sensor has quite a lot of applications. This is a laundry list of my group are focusing on. The application go from agriculture, medical, pharmaceutical, consumer, industrial, and the environmental monitoring. There's a very different kind of constraint toward this all different application. My group is mainly focused on something that require a planar PS sensor. Among them, for example, agriculture use, we try to put a PS sensor inside the cow's or sheep's stomach to measure the PS sensing, to know that if they are digesting food efficiently. And we working on wound monitoring, try to figure out that when you need to change the bandage. My group has been working on putting the sensor inside the stomach and esophagus to measure acid reflux disease. And also recently, we start working on sweat monitoring for either for patient that cardiovascular disease patients, or monitor the athlete sweat to understand the chemical when they exercise. And our technology has been licensed to a company that's working on cosmetic skin treatment. And then all this application has a very common thread, is that they require something very, very cheap, affordable, more importantly, planar application. So we envision that the sensor will look like a bandage that can be applied on the skin. So therefore that if you look at the PS sensor that's available today, there's three different types. Glass rod is the typical PS sensor, but you can see that it's too bulky to be included in a bandage. The optical sensor can be very accurate, but they require photodiode and LED, and that could consume a lot of power. So that may not be appropriate to be wearable or inside the body. And therefore that we're trying to make a planar sensing PS film. Among them, there are three different types of fabrication technique. One is using a target and spotter iridium oxide on the surface, or using electroplated method to deposit the iridium oxide film. For my group, we are mainly focused on sodium deposition, which I will talk about later, is because we believe that is the most affordable fabrication method. So let me reiterate the motivation. The motivation is try to make a PS sensor that can be conformed on skin or tissue. So mainly, it has to be flexible, therefore the substrate has to be flexible. So we have a first constraint already. And last year, we demonstrate the PS sensor, and this one is on a 125 micron polymer, and that can be conformed on curved surface. But then last year, we demonstrate an ultra flexible substrate that the substrate is only 25 micron, and that we can twist it, stretch, and even make a ring on the finger without affect the performance. All this demonstration, we done repeatability and reliability tests because it has to be very reliable, and we found there's an issue. And that is that the PS sensor, very often they are interfered by other ions other than hydrogen. For pH sensing, we are measuring the hydrogen concentration, but the redox of iridium oxide interact with the hydrogen obviously are affected by all this positive ion. And therefore that if your liquid, say sweat or blood, that have other positive ion, then you cannot avoid that sensitivity of the sensor now will be changed. And this is a big issue because our sweat has a lot of sodium. So we propose this method is that can we integrate multiple sensors on the same substrate and use a sodium sensor to calibrate the pH value? So we have three different electrodes on the substrate, and each of the electrode is 10 millimeter by 1 millimeter. This is just for demonstration purpose because the performance actually does not rely on the size, and we have demonstrated as small as 20 micron by 50 micron, as big as 10 centimeter by 10 centimeter sensor, and they have the same performance. We make a iridium oxide electrode that is to use to measure the pH value, and then we coated the iridium oxide with sodium-selective membrane to sense the sodium. And then we use the silver chloride as the reference electrode to be based. So I will talk about this in detail. First, making the iridium oxide pH sensor is very, very simple. We take a polyamide substrate. In this case, is 25 micron polyamide, very stretchable, so we have to put it on a solid wafer. Then we mix iridium chloride powder with alcohol and acid. Put them into the beaker and keep stirring it until they are very uniform. And then we dip this strip with the gold conduction line inside this beaker and dip it. And we take it out and dry it, and then we bake it at 325 degrees. So this is like a baking cookie, fairly simple. And after this is done, then we have two film that is covered with iridium oxide, and then we make the sodium selective membrane. The principle of the sodium selection is by size. So we select this polymer that's B12C4, and we dissolve sodium inside this solution. And after we make it, it will have a hole that allow the sodium ion to be catched. And the fabrication is also fairly simple. It's only involved the beaker. First, we take these two chemical, polycarbonate and tetrahydrofuran. Excuse me, I can't pronounce the whole thing. And we just keep mixing them until 30 minutes later that they look, the color look uniform. And then we add the DOS in there and we keep mixing it. This is to try to make a correlate that is soft enough to allow the sodium to be catched. And then we add B12C4 and the salt into this solution and keep mixing them. After we mixing them, then we just pour it or paint it on the electrode, the iridium oxide electrode, to coat them. And then we just leave it at the room temperature, stabilize this film. And this is a fairly simple fabrication process. And then after that is done, then we apply the silver chloride reference electrode on the substrate. We use a silver chloride paste. We paint it on the gold, and we bake it at 125 degrees for 15 minutes. So you can see that the fabrication process is fairly simple. You just need a few beaker, stirrer, and hot plate to make it. And this is how we test them. So this two silver chloride will measure the noise. This kind of noise comes from the ambience, the environment, RF radiation. So we take this signal and we take the pH sensor and the sodium sensor output and minus the noise that's being received. Then we can get rid of all the interference from the electromagnetic wave and get a true pH potential and sodium potential. And here's the, I need to speed up. This is the performance. First, we measure the pH sensor in pH equal to 4, 7, and 10 solution. And then we start adding sodium in there, and you can see that the performance the potential that's being produced start to increase. This demonstrates that the pH sensor is affected by the sodium concentration, no matter which solution is. And then we plot the potential drift by the concentration of the sodium, and you can see that they are a little bit different. For acid and neutral solution, the drift is fairly matched, but the alkaline, the drift is different. That's because in the alkaline solution, there's an OH radical which is negative charge, and that interact with the sodium, which is positive charge, differently from these two solutions. But this is obviously that the sodium will affect the pH output. And then we plot the pH versus the potential produced at a different concentration of sodium, and we found the slope are fairly the same. This means that the sensitivity of the sensor, no matter what kind of sodium solution is interfering, the sensitivity of the pH sensor remains the same. So this is a good news. That means that we do not need to recalibrate the pH sensor, just need to know the sodium concentration. Then we measure the sodium sensor at a pH equal to 4, 7, and 10. And in the solution, we add different concentration of sodium. And of course, this is sodium sensor. They should respond to the sodium when we add the sodium into the solution. But you can see that these two plots fairly are the same, but this one is not. Because this one, again, is alkaline. It acts a little bit different from the acid and the neutral. And this is showing that different concentration of sodium versus the potential being produced. And you can see that pH equal to 10 has less sensitivity for the sodium sensor. In our pH sensor, we demonstrate more than 3 years, and we always has a transition time that's shorter than 1.6 seconds. So we're wondering that if the sodium sensor behave very slowly, then that defeats the purpose of having a sensor. So we also measure the transition time of the sodium sensor, and we found the sodium sensor reach 90% of the final value at 4 seconds. So this means that we actually select 6 seconds as the standard time. So every measurement in the future, we measure at the 6-second point. Then that means that the pH sensor and sodium sensor will reach the final result. And then we also measure the silver chloride electrode at different pH and different concentration, and the data are exactly the same. So this is good news. That means silver chloride is suitable as the reference electrode for both of them. So then we take all this and put it into the data processing. We measure the pH solution with different concentration of sodium, and then we take the output from the sodium sensor minus the output from the pH sensor, and we found the data roughly clustered together at different pH value. And these are the delta of the potential for all different concentration of sodium. To put this into perspective is a comparison. The left one is the calibrated one, and the right one is uncalibrated one. Uncalibrated one, you can see that the pH sensor affected dramatically by different sodium concentration. But after the calibration, the drift of the voltage now become much smaller. Take this voltage and we divide it by the sensitivity of the sensor. We can find the delta pH between the uncalibrated and calibrated one. This means if I have a pH sensor that has no sodium sensor, I'm measuring pH equal to 4, but my result can be 5.56, which is obviously wrong. But using this calibration, and now that is converged to 4.33, much better than the original case. And here I want to mention there are multiple features of this. First of all, this is planar, this is a flexible substrate, and it's integrated. So we cannot compare this with existing high-end pH sensor. But most importantly is that we are doing all this measurement without cleaning the sensor. So usually when the manufacturer show you their performance, they test in different solution and they clean it with water and show you how great the pH accuracy is. But in all our measurement, we just dip into different solution without cleaning. So this result is much more realistic. But nonetheless, we take a commercial sensor and compare with the commercial sensor. We found with the commercial sensor, we added different sodium into the commercial sensor. We found that their pH also changed quite dramatically. For this one, pH is supposed to be equal to 7, but with a different sodium, it's supposed to be still be pH equal to 7, and you can get pH equal to 6.3. So that obviously has error. But with this calibration, we can now bring that accuracy to a very confined area without affecting by the sodium. So even compared with the commercial sensor, our performance is still better. And of course, this is just demonstration with sodium, and you can do the same thing with potassium and calcium, and that can bring the measurement of sweat or blood measurement to more accurate result. So bring this to a conclusion. We demonstrate a pH detection system. They have a self-calibration electrode, allow you to apply the sodium sensor information to bring you a better pH result. And this interference is much more dramatically reduced, and all these are demonstrated on this ultra flexible substrate. And that brings to the conclusion of my talk. Thank you very much.